Hello team, we're going to talk about Kubernetes, which is one of the most common container orchestration solutions today. So Kubernetes was originally developed inside Google, but it was open source later on, and today everyone can use Kubernetes, and it's what we're going to use for the programming assignments in this course. So Kubernetes is very complex because it has many functionalities, like we saw in the previous video. So it helps to understand the terminology that Kubernetes use when talking about it and when we go read the documentation. So a first concept we have in Kubernetes is that of a cluster. So in Kubernetes, a cluster is a set of containers and the orchestration software that's managing these containers. And the number of containers that's running on a cluster depends on the demand because of autoscaling and the amount of hardware that is available to run that cluster. And there are two layers of software in Kubernetes. One is the orchestration software itself, which is accessed by application developers, and application software, which is developed by application developers and accessed by end users. So putting this graphically, we have servers, then we have the OS and the orchestrator running on top of the servers. So the OS and the orchestrator are deployed by the cloud operator. Then we have the containers running on top of the orchestrator. So the containers are deployed by the application developers, and the application developers, they deploy the containers using the orchestrator. And the end user, this is us using an application, for example, we will use the application so they access the container. So each software in this stack has different players that interact with it. So the end users interact with the applications running on the containers. The application developers interact with the orchestrator to deploy their applications. And the cloud operator is in charge of deploying the orchestrator. Another important concept in Kubernetes is that of the pod. So Kubernetes manages pods. It doesn't manage individual containers. So the pod is the smallest unit that can be managed inside Kubernetes. And it's done this way because depending on the application you have, a single container will be insufficient to provide the functionality you need. In this case, you need to use multiple containers to provide the functionality. So this is what the pod allows. So the pod may be a set of tightly coupled containers that cooperate to provide the functionality. Although a pod can have multiple containers, it's very common for pods to have a single container, like a web server. So when Kubernetes decides to deploy a pod, it's going to place all containers of that pod in the same server. And the containers in the pod will communicate over the host's local network. So communication between containers in the same pod will not go over the network wires. It will remain inside the server that's running the containers for that pod. And the communication between the containers, remember, is eased by the naming and discovery service provided by the orchestrator. So a container can just call or access the other container by name. So let's discuss an example pod. So peering is a research project that I run with colleagues at Columbia University, and peering provides a virtual router that researchers can use to interact with the internet. So researchers use peering to run experiments. To implement this virtual router, we have multiple components. So we packaged these components in containers, and we have a pod that will run on a server. And the containers inside our pod cooperate to implement this functionality of the virtual router. So we have three containers, one running OpenVPN, which talks with the researcher, and two containers talking with the rest of the internet. So we have Bird for IPv4, and then we also have Bird for IPv6 because we support both versions of the IP protocol. So we have three containers in the end, and they cooperate to provide this functionality of the virtual router. So when we deploy peering, we deploy these three containers at the same time. If one of the three containers fail, then the pod doesn't provide the functionality that it's designed to provide. The Kubernetes documentation has another example of a pod. So here we have two containers. One of them runs a web server that services user requests, and users usually accessing content, and the content is stored in this volume. So the web server grabs content from the volume and sends it to customers. And in the same pod, we also have an auxiliary container that pulls updated content from a content manager and puts the updated content, say images, on the shared volume. So over time, this container, the file puller, will update content in this volume, and the web server will serve fresh content to the customers over time. Now, when we go deploy this application, we need to deploy both containers at the same time. So the construct of a pod allows the developer to specify that we need these two containers and a shared volume for the application to work. An application developer has to specify what goes in the pod. So we do this using a Kubernetes defined API. And this API, you can use either JSON or YAML to write a specification for your pod. And here we have an example. So a pod specification has a name for that pod, for example, Nginx here. And it also specifies what containers are in that pod. So in this specification, we only have one container. The name of the container is Nginx, and then this is the image, which is the software that will run inside this container, and Nginx is a web server. And we also have to specify the ports that the container will use. So this is a web server, so it will use TCP port 80, which is the normal port used by web servers. The container specification can also have metadata. So here we only have one item of metadata, which is the name of this pod, and the name is Nginx, but we could have other metadata. For example, we could say who's the author of the pod, how many containers it has, the last time it was updated, and so on. And we use this metadata for search and also as management targets. For example, we can decide to upgrade all pods that match a given name or that were developed by a specific developer. There's one special type of container in Kubernetes, and it's called the init container. So the init container runs before other containers in the pod. And it's usually used to set up the environment or to verify the environment before the other pods start. And if you find that there's something wrong with the environment, for example, you can just abort the application instead of letting the other containers try to start, and then you will have some containers fail and some containers start correctly, and you're gonna get, the pod will be in this unreliable state. So to avoid this, we can have a init container and check that the environment is set up for all of the containers in that pod. Let's go through an example. So here, going back to the pod example from the Kubernetes documentation where we have a web server serving images to customers, we can have an init container to get an initial set of images to pre-populate the volume. So when the web server starts, we already have some content in the volume and can start serving users immediately. And then the content in the volume will be updated over time when the file puller gets additional content from the content manager. We also have an init container in pairing. So in pairing, before we run the OpenVPN and Bird containers, we run an init container that sets up all of the virtual interfaces that we need to operate our virtual router. So we're going to create, multiple virtual interfaces for OpenVPN and also virtual interfaces so that Bird can talk with the rest of the internet. And we do this before we bring up the other containers.